शाम बखैर और आप सबको द ब्लैक होल में खुश आमदीद। अगर आपने कैलकुलस पढ़ी है, भले कॉलेज लेवल ही की क्यों ना हो, तो आप लिमिट्स, डेरिवेटिव्स और इंटीग्रल से लाजमी आगाह होंगे और यकीनी तौर पर आपका पाला जो है वो डी एक्स, डी वाई और डी जेड, ये जो सिंबल्स हैं इनसे पढ़ा होगा। फॉर्मली known as differentials and informally known as infinitesimals या infinitesimally small changes in the variables x, y and z, जैसा कि dy dx को टेंजेंट लाइन की स्लोप कहा जाता है, जैसा कि मुझे अपने कॉलेज का वक्त याद आता है। तो गोया ये फार्मूलों में रखे हुए कोई बेमानी या गैर ज़रूरी सिंबल्स नहीं है, इनकी अपनी एक अहमियत और सिग्निफिकेंस है और आज हम यही जानने की कोशिश करेंगे। उन्वान आप मेरी पुश्त पे बोर्ड पे लिखा हुआ देख सकते हैं, what dx and dy really are, और गोया we are going to confront dx and dy head on, directly and precisely। और इसमें हमारी मदद करेंगे हमारे आज के गेस्ट स्पीकर डॉक्टर मुख्तार उल्लाह साहब, जो मेरे दाएं जानिब तशरीफ़ फरमा है। आपकी बीएस है इन इलेक्ट्रिकल इंजीनियरिंग, डिस्टिंक्शन फ्रॉम यूईटी पेशावर। उसके बाद आपने नेस्कॉम को ज्वाइन किया, you received the prestigious TROSS award, then you completed MS in advanced control and systems engineering with distinction from the University of Manchester, then you joined University of Rostock Germany, जहाँ आपने सर्व किया एज रिसर्च साइंटिफिक ऑफिसर, डॉक्टरेट मुकम्मल की इन सिस्टम्स बियोलॉजी एंड कंटिन्यूड योर पोस्ट डॉक्टरल रिसर्च until 2013। पाकिस्तान वापस आए, फिर आपने ज्वाइन किया फास्ट नेशनल यूनिवर्सिटी ऑफ कंप्यूटर एंड इमर्जिंग साइंसेस, जहां आप सरदस्त प्रोफेसर और डीन ऑफ इंजीनियरिंग की जिम्मेदारी निभा रहे हैं। आप स्प्रिंगर टेक्स्ट बुक के ऑथर हैं और आपके 40 से ज़ायद रिसर्च पेपर्स जो हैं स्पैनिंग कंप्यूटेशनल बियोलॉजी, कंट्रोल सिस्टम्स, सिग्नल प्रोसेसिंग, पावर सिस्टम्स, ऑटोमेशन, टेलीमेट्री, रिमोट सेंसिंग, एग्रीकल्चर एंड इंजीनियरिंग एजुकेशन वगैरह के मौज़ूआत पर हैं। कई डॉक्टरेट और एमएस स्टूडेंट्स जो हैं उन्होंने आपकी सुपरविज़न में अपनी डिग्री मुकम्मल की है। आप की रिसर्च कोलैबोरेशन है विद नेस्कॉम, with the University of Rostock, as well as University of Hull, UK, and the University of Lincoln, USA, in areas including AI, control systems, and statistical modeling. आप सब लोगों की आमद का शुक्रिया। थोड़ी सी जहमत करके अपने सेल फोन स्विच कर लें टू साइलेंट मोड सो दैट देयर इज़ नो डिस्ट्रैक्शन। गुफ्तगू के बाद हस्ब रवायत फ्लोर ओपन होता है फॉर Q&A। जब वो मरला है तो आप बस अपना हाथ बुलंद कीजिएगा, माइक्रोफोन अपने तक आने का इंतज़ार कीजिएगा और आप जो भी अपना तबसरा, सवाल या क्वेरी हो वो बिला झिझक रखिएगा। ये क्लासरूम इन्वायरमेंट यहाँ पर नहीं होती, यहाँ पर आप किसी भी दर्जे का सवाल कर सकते हैं, क्योंकि वो सिर्फ आपका सवाल नहीं होगा जो हमें ऑनलाइन देख रहे हैं या जो हमें बाद में देखेंगे, हो सकता है वो उनकी भी एक क्वेरी हो, तो आपके ज़रिए उनका मसला भी हल होगा। एंड दैट्स इट। तो चलिए डी एक्स और डी वाई वगैरह की वो हकीकत जानने की कोशिश करते हैं जिससे आमतौर पर हम पूरा कैलकुलस कोर्स पढ़ने के बाद या पूरी डिग्री लेने के बाद भी शायद लाइल्म ही रहते हैं। प्लीज़ वेलकम डॉक्टर मुख्तार उल्लाह।
Acha, can you hear me now? Okay. So I would need the projector for the first few minutes. Yeah, but before that, let me introduce you to this topic and primarily the motivation of why I got interested in this. So I assume that most of you are already exposed to calculus in some stage of your life. You must have solved calculus problems, and if you can recall, The most important thing which you must have heard from your lecturer or school teacher is that, okay, we will write dy over dx, but you're not supposed to see this as a ratio of two things. Yeah, because they are always discouraging you from giving meaning to dx and dy. Because it's a limiting process, you all know that. So, to remind you further, actually, the limiting process starts from delta x and delta y, yeah, and they represent small changes. And then there is a limiting process, and when you force delta x and delta y to approach zero, and you're told, okay, approach zero, but don't touch zero. So one thing is very clear, that it is not allowed for delta x and delta y to become equal to zero, because then you will have zero divided by zero, which is nonsense. So that is something which you already know. And that is the reason you're not supposed to give any meaning to delta x, because if you say delta x, I I take the limit independently. So, I mean, when I was learning it for the first time, I expected dx to be the limit of delta x, which is a natural thing to occur to you. But if you try that independently, I mean, because you are making it smaller and smaller, so the limit should be zero, right? And you said you're not supposed to touch zero. So then, how do you stop? Do you stop at 0.01? Do you stop at 0.0001? Do you stop at 10 to the negative 100? Do you stop at 10 to the negative million? And you're not supposed to ask that question. So one thing is very clear, that if you talk about delta x, you can clearly say that it is a small number, right? Because you don't want to specify it. And there is nothing wrong with it, because your delta x may be 0.01, my delta x may be 0.001, and we are both happy, because we don't stress a unique value. But when it comes to dx, we want to give a specific status to dx, and we say, okay, this is the point where it is as small as possible without touching zero. So the mathematician started asking these questions, that what do we mean by dx, right? So it turns out, now let me show you. Don't blame yourself if you don't understand this, because can we, okay, yeah, sorry, I need to change the settings so that it doesn't go. If you think that um, I or you are the only one who don't understand this, now I'm sharing these two paragraphs from a guy called Spivak. Okay, Michael Spivak. He is an authority on calculus. If you read his books on calculus and many other topics, and if you see his citations, you will soon come to know that he is a very serious mathematician. And this is what he writes: classical differential geometers, right, did not hesitate to talk about infinitely small changes. So they used the word infinitely small when they wrote dx or dy, right? Just as Leibniz had. So primarily Leibniz was the main guy. No one wanted to admit. Now this is the main thing, that this was nonsense. This was nonsense. Yeah, but they were still using it. Why they still kept using something? A very similar argument I shared just a while ago with one of my friends is that a similar argument was given by I, imaginary unit. Why was it called imaginary number? Because the guy who introduced this, he didn't know what it means, but it worked. Yeah. So he introduced this only as a shortcut to solve an algebraic equation which otherwise was impossible to solve. So it worked for him, but he had no idea, and it took other mathematicians more than 200 years to determine what that I means. Yeah. So don't force you into thinking that the one who invents something knows what it means. Yeah, because invention can be for many reasons. So that guy was in trouble. He wanted to solve an equation. He did not have any method. He introduced this tool. He called it imaginary. And why did he call it imaginary? Because he didn't know what it means. But later on, it turns out that this I, which we call imaginary, is as real as any other number. So same is the story here. Leibniz, Newton, of course, Newton was not a fan of dx. He had his own notation, but he actually he had to use this notation in order to communicate with fellow mathematicians and physicists. So people kept using these symbols, and you can see that they didn't want to admit, but they knew from inside that it was nonsense. Because you cannot answer the question, what is dx? Tell me the value. And they say, okay, no, you can't ask for the value. Okay. So because true results were obtained when these infinitesimally small quantities were divided into each other. So if you divide one small number by another small number, you get the result. But the problem is, I can give you 4 examples, and every time you will get a different answer, and every time the numerator and the denominator will be as small as you like. So you cannot guarantee a unique result. So there was something fishy, right? So I don't want to repeat this thing, but this was the reason why people got interested into it. And the 20th century mathematicians, I don't want to get into history, because once you understand today's lecture, I expect you to actually search it for yourself, and you will find the key players who solved this problem. So I'm going to actually report that to you. So before I get to dx and dy, my plan will be that I'll first question your understanding of delta x and delta y. Because the reason we don't understand dx and dy is because our claim of understanding delta x and delta y is also wrong. And that mistake is actually the reason why we don't get dx and dy. Then I'll follow it up with another question. Before you say delta x and delta y, you need to ask yourself, do you understand the meaning of x and y? So when you have a coordinate system, right, you typically write x on one of them and y on the other one. And many of us are into this illusion that we know what those symbols mean. And I'll convince you that that is also wrong. Yeah. So not understanding x completely is the reason we don't understand delta x. Not understanding delta x is then the reason why I don't understand dx. So we first have to take x head on. Now, the reason I didn't want to use x and y in my lecture, you wouldn't be here if I used that. So that was not catchy enough. So the reason we don't get dx and dy is because we don't understand delta x, delta y, and then x and y. But before that, let me just show you one graph in which I will request you to change your perspective of when we talk about derivative. So if you have a function, for example, f, you typically say f prime or f dash is the derivative. And most of you must have, you can now recall that there is a limiting process. You first draw a line, which is the secant line, and then you change that line and you make those 2 points. Because the reason you call it a secant line, because that line will intersect the curve you are interested in at 2 points. And those 2 points are distinct. So let's start with that, because this is too abstract. So I'm now writing something in GeoGebra, and I'll write the thing which most of you are happy with, x squared. So this is a parabola. So let's choose, so I'll just write m. The good thing in GeoGebra is that when you type m or anything, it automatically has a scale for it. So I can now change m from, let's say, -5 and +5. And let's say I type a. So now I have 2 numbers, m and a. So now the limiting process which you have studied in your school and college and university is that you start 2 points on this curve, you join them by a straight line, and that line is what you call a secant line. And then you fix one of them and bring the other point closer and closer and closer and closer. This is what you mean by the limiting process. And in so doing, what changes? The slope changes, right? And when these 2 points actually touch each other, you declare that to be the tangent line, and that slope is what you call the, tell me. So far we were calling it a slope. Now you call it derivative because it's a special thing. Slope is not special, yeah. Slope can be of any line, but this is not just any slope, yeah. So that's why you have to give it a name so that, yeah, you recognize the status of it. So derivative. Now I want to turn this, and you remember that this is what you mean by delta x approaching 0, right? Because you want to make these 2 points. But now the problem with this limiting process is that you're not allowing these 2 points to touch each other. Because the moment they touch each other, delta x will become 0, and then the whole math will stop working. That is the reason why I don't like that picture. That picture is good for solving problems, but that is not good for understanding the problem. So now I want to change your perspective, the same problem, same curve, but I want you to think about it in a different way. Assuming you know how to do it, but the thinking process has to be different. So now my m here is the slope. And if I change this slider, I change the slope, right? Negative slope, positive slope, 0. And I want to use this a for a point on the x-axis. I have to fix a point. So I'll just be calling that. And I want to be able to change that as well. So yeah, so a will be different values, right? And now let me do something. Now I want to create a line. I now want to write an expression for a line. And I want you to help me if you get this, right? So how should I write an expression? Because you know how to write an expression for a line, yeah? Y equals mx plus c. That form is good, but it's not good here. I want this line to pass through one point. I want to force it. And where? I'll use a for that. So for example, here, what is the value of a? 1.2. So how should I write my equation so that the line must pass through the value of this function at a, which is 1.2? So how should I do that? I can't just say mx plus c with any value of c. So it suggests that that form y equals mx plus c is not the right form, because the c is the y-intercept, right? The problem I am going to solve here requires x-intercept. I want this line to pass through a point on the curve at a specific value of x. So I need x-intercept. So it turns out that instead of c, I'll use a for that purpose, right? So now I'm just writing this. I want to write f of a. F of a is the value of this function at a. I want this to be the case no matter what. So this should be the value when x is equal to a, right? And any other value must be because x is different from a. So the next term should be, watch carefully how I construct this. I need to have a term x minus a. That will tell me how far I am from a. So when that x minus a is 0, my value should be f of a. And you see, it seems correct, yeah? Set x is equal to a, that term gets 0, you get f of a. So I'm now forcing it. Now the question is, what should I multiply that x minus a? If I don't multiply, it means it will be 1, and 1 means that the slope will always be 1, because mx, right? So I don't want 1, I want, so it's not mx plus c, it is m times x minus a plus f of a, right? So f of a will make sure that no matter what the value of x is, one of the point will be f of a, and the second point will depend on how far x is from a. And m will determine the slope of that line. So now the line you see has a slope 0.6 because m is 0.6, and it, remember, it intersects the curve at 2 points, but one of them is already fixed. Which one of them? 1.2, remember? So the point where it intersects to the right of the vertical axis, that has been fixed by this f of a. The second intersection is a consequence of our choice of the slope. So now if you want to see, and this is something which you must understand, because without this, this whole thing is, I mean, it's impossible to follow. So let me change M now. Yeah. Remember, the intersection on the right cannot change because I have fixed it. No matter what the value of M is, it has no influence on f of a. It only multiplies x minus a, right? So there is no way I can change the other. Yeah. So these are all positive slopes. This is now zero slope, and this is now negative slope. Now let's see how things change when I change a. So let's fix M, and let's change a. Only when I change a, the second intersection changes, right? So is this clear? Can someone tell me why can't this line come below? So I'm changing this. It goes up and down, but the moment it reaches the last point, it cannot go below. Why? Why does it come back?
क्योंकि हमारे पास ग्राफ पैराबोला है और उसकी वैल्यू 0 से नीचे तो है ही नहीं।
नहीं, बट ये तो लाइन है ना, मैं ग्राफ को तो मैं
नहीं।
प्लॉट ही नहीं कर रहा।
नहीं तो जो हमारे पास फंक्शन है वो हमारे पास आई फर्स्ट 2 कोऑर्डिनेट्स में है, तो नीचे वाले 2 कोऑर्डिनेट्स में तो वो एब्सेंट है, तो लाइन नीचे
No,
कैसे
you need to tell me the thing in this equation which is stopping that from happening. I have fixed f of a. No matter what, it has to. So because of that, there is no way. Because if it drops below, then it will have no intersection. And I have made it literally impossible.
यस
Yeah, so exactly. Yeah, no, but f of a, it's not just a, it is f of a.
एफ ऑफ ए यस
F of a is the value on the vertical axis. I have fixed that f of a. Yeah, so there is no way this line can come down. Okay, for example, if I change this f of a to something arbitrary, then I can do that. For example, I can change this to, no, I don't want to destroy that. Let's say I do this 2 plus m x minus a, right? And let's create another parameter, right? Sorry. Let's write b here, right? And instead of 2, I just write b here, right? And let's change b now. Now I can do whatever I want because I have the freedom. But when I change this b to f of a, f will determine what is possible. My fingers cannot dictate this anymore. So I would highly recommend you, whenever you are doing math, you should know what is happening. Yeah, it's not just solving problems. So anything you write, you must have a clear meaning in your head, right? So anyway, I can now remove b. Okay. So now let's fix the value of a to 1.4 or whatever the value is, and now I'm changing. So these are all secant lines, right? Watch closely. The point on the right is fixed. By changing the slope, so now let me ask you a question before I do this. I'm looking for that special value of m. So no matter what I do, there will always be two intersections. You agree? Yeah, because the type of curve is that they differ, but I am looking for the value of m where these two intersections touch each other. And this is a different kind of process. This is not a limiting process. This is a geometric process. So if you were doing this by delta x approaches 0 or a approaches b, in that process you're not allowed to touch it because then it becomes 0. Here, you can imagine geometrically, you can solve these equations because one of the equations has x squared in it. One of the equation is like of a straight line. You know how to solve simultaneous equations, right, from school. If you go home and if you solve these, and if you make a condition that the intersection should be such that both the intersections are at the same point. It is possible. You can even solve that. And that is what I'm doing now geometrically. So now I will look what happens. This is now. And now we declare this as the, so far we were calling it tangent lines. Now this is, no, sorry, secant lines. All the previous lines were, now it is a. So now how should we define a tangent line without limits? The line in which both the intersections coincide. No limit. You are allowed to touch. These 2 points are allowed to be, and you must have solved algebraic equations. What if I ask you to solve x minus a bracket times x minus a and bracket equals 0? What is the solution to this equation? So I think because I got this point, I can now move to the board. Yeah. So this was the thing which I wanted you. The reason I wanted this illustration is to remove this myth of limits. Solving a problem in the language of limits is a limitation of that method. It doesn't mean that that process cannot be bypassed. This illustration literally bypasses this process because there is no limitation on these 2 points being on top of each other. And I can ask you to take 2 equations. One of them will be linear, the other will be quadratic. And you can say, okay, solve for the intersection. And then you put a condition that these 2 must be repeated solutions, or distinct solutions and repeated solutions. So it is possible for these 2 points to be on top of each other. And that special slope is what we mean by the derivative at that point. And that line is what we call the tangent line. All the other lines were secant lines. So, and if you don't get my point, just imagine in your head x minus, let's say x minus 2 in the bracket, and then x minus 2 in the bracket again, multiply these 2, set it to 0. If I ask you, what is the solution to this equation? X is equal to 2, but twice, not once. So this equation has 2 solutions, 2 and 2. On top of each other, no limit, no limiting process. And why can you do that? Because you are solving this in a process of algebra which doesn't require limits. You're not saying, oh, 2 approaches 2, or 3 approaches 2. You're bypassing that process. So geometry allows you to bypass that limiting process, which was fantastic for solving for the derivatives. You compute derivatives, but that process is actually a handicap for you to give meaning to this thing. Because we are interested in meaning. I'm not going to solve questions for you. I'm not a tutor in academies. So I am only interested in the meaning. Yeah. So let's get to that part now. If there is any question in this, I can get back to GeoGebra. Because I require this understanding for the next thing, right? So we need some should I remove all of it or just part of it? This one? This one? So now we have to start with x first, because the understanding of x is problematic. So before we start, I would like you to think that whenever I write something on the board, or whenever you write something on the board, on a piece of paper, you must ask yourself, what is the type of that thing? Is it a number? Is it a set? So for today's lecture, I only need 3 types. There are many types, but 3 are the only. So a number, you all know what a number is. I don't need to remind you that. You also know a set, it's a collection of objects. Yeah, a collection of numbers or a collection of shapes, anything. And what is a function? A function is a rule of assignment when you pick a number from one set and you assign it a value from another set. And if this is done in such a way that only one value can be assigned at a time, you cannot assign 2 values to one object, you call it a function. Otherwise, you call it a relation. So we're not interested in relations, we're only interested in functions. So whenever I write something, whether I say it or not, you must process it in your head. Is he writing a number? Is he writing a set? Or is he writing a function? Because without that, this thing cannot be solved. So now let me draw these 2 x's which you have been using so throughout your life. I'll now write x here and I'll write y there. And now I'll ask you, what is this x? Is it a number? Is it a set? Is it a function? The problem starts from here. Set. Yeah, set of points. So it's technically correct. There's nothing wrong with this. And I'm very happy that you didn't say number. So this only reflects your seriousness in this subject. Many people think of it as a variable, and when we say variable, we mean some unspecified number which we can change. So then we say, most of the people, they have in mind a variable. And when they say variable, they say, okay, this x can be, for example, 1. For example, this is 1, right? So this 1 means x equals 1. This 2 means. And I have seen people, this is not so bad, I have even seen people writing x here again for solving some problem. They use the same symbol x because in the back of their minds, x is some unspecified number, because that is how you define a variable, right? When you solve an algebraic equation, x squared plus 2x plus 3, that x is an unknown. And when it is an unknown, it is still a number. Whether you know it or not, you know it when you solve the equation. Yeah, just because you write x doesn't mean that it's not a number. That meaning of x is not here. It is not an unknown, right? It is something else. So it means that technically it is wrong with having a label x here. It is wrong to write an x here again. And it is also wrong to write that thing. What does that thing mean? You have an equal sign. On one side you have a number. On the other side you have something which is not a number. How can you have an equal sign there? Right? So that's the whole thing. We never question that. So now, coming back to your suggestion, it's perfectly okay, but unfortunately it's not useful. We need to go for a thing which is useful. So now I'll illustrate and I'll see why declaring this as a set is not very useful. So before that, let's have an experiment. Let's use x, and there is nothing special about x, by the way. So let's change this to h. I'll tell you why. And let's change this to m. So m for the mass and h for the height. So if I now ask, let's say you, do you remember your height? And when I use these symbols, I have already decided about the units because I'm not supposed to write units. So when I say h, it means height in, let's say, feet. Let's agree that h represents height in feet and m represents mass in kilogram. Because if I say mass, then I have to write kilogram every time. This is another mistake. Yeah? This m cannot be mass. It has to be mass in, because only then I can only write clean numbers. I don't want to write kg every time. And I don't want to write feet every time. So by chance, do you remember those 2 values? So let's say this is 5.8. And you can fake it. Okay, 75. Okay. I did this thing, okay? This should be enough hint for you. What do you mean by H? So typically we would do this, right? So, sorry. Typically we will say M equals what? 5? Not kilograms, because we defined M to be the mass in kilograms. So we don't need to write this again. And we typically write H to be my claim is that this is nonsense. This is only acceptable if M and H are unknown numbers. We use, the meaning has to be derived from the language. And who can understand language better than you? So when I say, how will I say it? He's my friend Abdul Basir Qazi, right? So think of Abdul Basir Qazi as an object or as a system. Yeah, in physics and thermodynamics, when we want to study something, we declare that as a system and everything else becomes the environment. So let's say in the whole universe, I'm only interested in Abdul Basir Qazi and nothing else. So what have I done? I have taken that object, and when I take that object, this object comes from a set, the set of individuals, the set of humans, the set of men. You can think about any set. And I have assigned a number to this object. So what is going on? Can you now tell me what is M? M is a function which assigns a unique number. This Abdul Basir Qazi will have only one value of M at this point. I cannot assign two values of M to him. And the reason, so you must be asking, why am I stressing that it is a function? The reason this function concept is important is that I am not only interested in Abdul Basir Qazi, I want to use the same M for Dr. Naqib, for example. So can you, for example, you. So now how will I write it mathematically, correctly? It will not be M equals 75, because when I write the same thing for you, I'll again use M equal, and that will be a different value. And this is the reason that meaning was wrong. M cannot be an unknown, because that unknown, even if something is unknown, it will still have a fixed value. So you cannot have two values for the same M. So the correct value, I don't want to say M1, M of Abdul Basir Qazi and H of. And when I write this thing for you, I'll not be making any mathematical mistake. M of Dr. Naqib, H of Dr. Naqib. Yeah, and this is why what makes it useful. That set thing, people must have thought about it, but it doesn't capture this thing. Why do we have this X and Y? Because we want to represent the physical, real world. We want to solve real world problems. We don't want to do math in vacuum. So, by the way, anyone who is a physicist, they already have a name for these things. They call it observables. So this is the process of measurement. You take something in the real world, you assign it a value. Computer scientists, they call it encoding. They use encoding. So you can have different names for it. So next time, whenever you see X here, so now I can get back to that problem. Now you must be wondering why you didn't see this before. And don't think that I'm making this up, okay? I learned this the hard way, because these questions were bothering me for many, many years. And I came to this place only after I sorted this out. So I didn't invent anything. I only made an effort to crack this from the literature. So now I can get back to your favorite symbols, X and Y. So the question is, why were you not exposed to this? There are two answers, two possible answers. Those who were teaching you, most likely they didn't know it, right? And let's say by any chance, someone who knew it, he didn't want to expose you to this because this was too complicated, because this needs a high level of maturity to appreciate this, right? The third reason is convenience. Just like in Urdu, Punjabi, English, most of the time we say wrong things, but the person, who is listening to us, they understand it. So many of the things we say wrong, but when you go to a court, yeah, when you become a lawyer, then your language changes. So it's possible. These informal, so when you say x equals 2 or m equals 10, this is the informal way of writing it because you don't want to write that detail every time. Nobody wants to know who the value was assigned to. Yeah. So informally, you can say x is equal to 2, y is equal to 3. But whenever you want to be precise and we want to address this question, you have to actually make it clear that, okay, it is actually a function. And I don't want to, so it's like, the mathematicians call it the abuse of notation. So as long as you recognize that it is an abuse of notation, I have no problem with that. But if you stress that no, x is a number, then there's a problem. Right? Now, why it matters? Now we can move on to delta x. Right? So what do you mean by delta? Forget about x. Whenever we say delta, what do you have in mind? Some kind of change. Small change, large change, people even use delta for large change as well, right? So change, think of delta as a change. Just like when I asked you mass of, so mass itself was not a thing, mass of something. So the moment you say of, it becomes a function. And by the way, let me give you one example of what convinced me, because I didn't want to accept this view. You don't think that I got it in an easy way. I was not willing. But then I saw one line in a chemistry book, and then it actually became very easy for me to accept this. Yeah? You must have seen in chemistry books how they write molecular masses or atomic masses. So let's say they will write C12, right? Carbon 12. Go to your chemistry books and you will see this. This was enough for me to accept this view. Mass of carbon atom. So, because then you can say mass of hydrogen, mass. So if you insist that mass is not a function and it is a number, then you're lost. Then you will have to write m equal every time, and nobody will know which atom you're talking about. Right? So delta. So whenever we say delta represents change. So change in something, change of something. So this should, whatever I explained so far, should be enough to convince you that this delta, when it applies to something, you should also expect function here. Yeah? It itself cannot be an absolute thing. Yeah? So it means that if let's say I have a graph, right? Let's draw a graph. Any graph. And I'll pick 2 points, right? Let's call this A. So now I'm using the symbol A, but this A is a number. Yeah? And X is a function, and X of something equals to A, and I don't want to talk about that thing. So that should be clear now. Okay? And let's say there is another point, B. So when I move from A to B, I want to know how this graph changes. So at A, the value of, and let's call this F. This is now another important concept of remembering if you don't want to get confused. When you label these x's, these are actually coordinates. They're also functions, but they're coordinates. Never write the function here. So it is not allowed to write this f there, because f is a mapping between x and y. So you can only label the graph with f. Yeah. So here you write y, and on top of the graph you write f. And don't write f of x. That is wrong. Why is f of x wrong? Because x, you apply f to x, right? And f is the mapping from x to y. So only label a graph with the name of the function. So now, at A, the value is f of a, right? F of a. And at b, the value is f of b. So what do we have in mind when we want to write delta? We want to have this difference. When a changes to b, f of a changes to f of b. So first I'll write the right side and then I'll write the left side, because the problem is how to write the left side. So f of b, f of a is what you want to call the change. So to call this delta will be stupid, because you will have to write delta every time and it will be a difference. So delta of something. Now the next thing, delta of what? So delta y, yeah, that is what many people write. But the problem is, here you need to understand one thing, and this is a very important point. Just like in a movie, you have a hero, right? And all the other things are extra. So the hero in this figure is the graph f. There is nothing special about x and y. I can change x to z and y to w. As long as the relationship is the same, it will still be the same function. I don't care what I call here. I can even write y here and it will still be the same function. Many of you will not be comfortable with that. There is nothing, because naming x, y, yeah. I mean, let's say this is current and this is voltage. This will be I and it will be v, but it's still the same function. So x and y cannot determine the meaning, but f can. So it is more reasonable to apply delta to f, because you want to change in f. This y you will see y in another graph as well. You're not interested in that thing. So the only reasonable way of defining delta, because you know why this matters. When you want to define a function, by definition, it is a rule of assigning numbers to numbers or objects from a set. You have to choose that set carefully so that it becomes a useful thing. So delta, if you apply it to y, it will be less useful. But if you want to make it more useful, make delta applied to f. So it is delta f, but it is still not complete, because delta f itself does not have any information about a and b. I have chosen a here, b here. So if a is here and b is there, then the delta f has no mechanism of tracking that, right? So I need to write something on the left side which not only represents the change, but it must. So it means that it's a more complicated function. That x was easy. X of this person is this, y. This is more complicated, because here you need the information about a and b as well. So what will you suggest? I want you to actually fill this, and then if we can make it more useful. So maybe you can give a first draft. It has to be delta f. So it means that f is a function. Delta f will also be a function. So it has to act on something. So by the way, if f is a function and if delta f is also a function, then delta cannot be a function. We mathematicians use a different name for it. They call it the operator. So an operator is a thing which acts on a function and it gives you another function. And your most favorite example is the derivative operator. What does a derivative do? It starts with a function and it gives you another function. Let me just write this down, because this is important. So let's say I have the function sine. I'm deliberately not writing sine x, because when I write sine x, that will not be the function. So what should I write to take the derivative? D of sine. Just like I say. And so sine is a function, but d is not a function. D is an operator which turns a function into a, and that function is. So I want you to be bold enough to write this without x, because the moment you write x, it means that you're not sure. This is the perfect way of writing it, because you clearly know that there is something which acts on a function, it gives you another function. Yes. I'll get to that. The meaning will change. Because D, remember, in the beginning, I requested you to be very specific about types. So if you write sin x, then D cannot have this meaning, because then D has to. So let's change this. If I want to write sin x, and you have to promise that x will not be a number, x will be a function itself, coordinate. So if this x is a coordinate, then sin x, although it's not, I mean, by the way, it is also a function. Because if x is a function, sin of x will also be a function, but not because of the sign, because of x. Why? Because if I change this x to a fixed number, I'll get a number. So when I write sin x, I have to thank x for the nature as a function. Sin loses its meaning whenever it is applied to a number. So let's say I change this to x, and because x is a coordinate, sin x will also be a coordinate. That's why we call it y, right? We call it y. And now I want to have a similar operator for that as well. So here I would never write D here, because this is a different type of object. So many people, I know what I mean, but because these two are different, so typically you must have seen a subscript there. Subscript declares it to be, it will still give you the derivative, but you are now dealing with a different object. And what is the answer to this now? This is now cos x. Yeah. So be specific about types, and then you will never get it wrong. Because that D, remember, whenever you define a function, when I define D as an operator, I must decide the domain and the codomain. So when you define D for those functions, you cannot apply that same D to a different type of object. Yeah. So I mean, this is the domain and the codomain are part of the definition. Just like sin itself. Think about sin itself. What is the domain of sin? The real numbers, right? So you cannot apply sin to, for example, alphabets or strings, or you cannot say sine of a triangle. Can you say sine of a triangle? Sine of a triangle is a legitimate object, but it does not belong to the set of objects for which you have defined sine. So similarly, D also gives you derivative. Dx also gives you derivative, but derivative is informal. Derivative is the informal thing, right? When you say formal, dx on one type of objects, the function itself. Dx applies on another type of function, which when you apply sine to a coordinate, so basically dx acts on coordinates and d acts on the functions directly. Okay, so let's get to this now. We need to settle this now. So delta f, what should I write here to represent, because we can't write something. So f is a function, delta f is a new function. Delta is the operator. So delta f has to act on something to give you f of b minus f of a. The question is, what should be that something? And you can give me suggestions. You need these two numbers, yeah? You need both a and b. So your first guess will be to define it as a function of two inputs, a and b. The first input will represent the first point, and the second input will represent d. So now you know the meaning. Yeah? Not only you must apply delta to a function, then you must apply delta f to a different kind of object, and that object must have information about both a and b. If any of them is missing, this equation will not be sensible, right? I mean, there is one thing which we can improve here. We don't want to define this as a function of two variables. That's complicated because we want, this is a function of one variable, so we would like this to be defined as a function of, to make our life easy, because when we go to multivariable calculus, things are going to become challenging anyway, so we don't want to carry this challenge. So any idea how to simplify this? How to make it a function of, yes? No. Your first guess will be the change. What is the change on the x-axis? B minus a. So it is a function of b minus a. But there is one thing still missing. B minus a only tells you the change. So b minus a cannot distinguish between, what if I move this a and b here? So let's say this is a prime and this is b prime, and I'll write b prime minus a prime, and what if these two values are the same? I have no way of distinguishing these 2 points from. So it means that the change will just be one piece. I must provide the other piece as well. And where I am defining the change. So the change is defining, you are defining the change at A. So actually you are replacing, there is no free lunch, yeah? If you want to replace A comma B, you have to replace it with 2 pieces. You cannot replace 2 pieces with 1 piece. So actually, instead of A comma B, you want A comma, so A tells you where, and B minus A tells you how much is the change. That change at A. So what the mathematicians have settled, this A is a parameter. This tells you where to start this process. So they write this A as a subscript. So now you have different versions of delta F. Delta F alone has no actually knowledge about where to start. So what you write here will tell you where to start. What you write there. So now I can replace that B minus A with, for example, your favorite symbol H in calculus, yeah? H approaching 0. So this will be, what should I do here? Because this A will come here, and this will be, this is the next point, B. So this is A, and this is H. So it is A plus H. You're not supposed to write B. Why? Because you change the type. The type is important. This is supposed to tell you where you start. This is supposed to tell you the change. So you cannot write B. B is not the change. B is the final point. So here was B minus A. It was not B. So it has to be A plus A, because A plus H is the new value. A is the old value. So f of A plus H minus f of A. So now think about this carefully. We actually rediscovered delta. Delta is an operator. It has to act on a function. And you have to act, when it acts on a function, it turns it into another function, which we call delta F. And that delta F, because it is itself a function, it has to act on these points in such a way that you get a function of a single variable. It is a function of a single variable because we want to keep this A as a parameter. Yeah, because we first choose the point. If I want it here, for example, there, how will I change this? At that point, it will be delta F, and here LT, A prime. This prime is not the derivative, right? Sorry, that is a different thing. Even this you can solve. You know, whenever you have this conflicting notation, you use prime for derivative, right? How do we convince ourselves that this has no clash with that? Again, the type will help you. Newton defined that prime for functions. So when you apply it on a function, only then it means derivative. A is not a function, so A prime cannot be the derivative. So thinking about types will clarify many of your confusions. We don't do that, right? So of, I can use the same h because h is still the change. I don't care whether h is this one or this one. So this will be, how will it change? F of A prime plus h. Now you have a recipe of precisely, so you see, you're not discovering any new way of computing. You know how to compute change. You're rediscovering of representing that computation in a precise way which removes all your confusions. So once we are clear about delta f, first we clarified the meaning of x and y, now we clarified the meaning of delta f, and once we learned that we define delta only for functions. Now the question is, how do we make sense of delta x? Because you see delta x, you don't see delta f, right? You also see delta f, but in advanced courses. So now we need to take this understanding and export it to define delta x in a precise way. Are we ready for that? Yeah? Or we need a break? Okay, so let's change it. So now I'll write delta x and you are going to help me what it could mean. Think about it. Keep that same meaning of delta. Yes? This is minus. This one? This one? This is plus this one? This is a plus h. No, look. What is the meaning of this thing in the subscript? The first point, right? That is the first point. They are both on the left side. They are both negative, but I don't care. This change is still from A prime to B prime. So this h is still positive. Huh? So this h doesn't depend on where these two are, right? So it's always from left to right. Left to right. This will be minus h if I declare this as my A prime. And this is my B prime. That will be, but then h, even h can be negative, remember. I can still use this thing, but then h will be negative. But that is something that you can deal with. That's not an issue. But let's get to this thing now. Yes? No, there's no equation. Remember, you can change this f to any function you like.
I mean, like you have described there is a path, and then you are explaining the two equations with respect to that path, right?
Yeah, but you can change this path to any path you want. There is no limitation here.
If we change the path, for example, if we explain the same scenario
So
in the case of
let's
semicircle,
let's do it this way, yeah? So let's say this is A, right? And this is B. It would still be A plus H equals B.
okay.
There is nothing in this graph which limits the applicability of this concept.
So this is applicable for in every situation.
Everything. It's a generic thing. You just need to get it right. So I mean, if you are confused, you can work it out at home. What you need to pay attention to right now is to remember the types. Delta is an operator which must act on a function.
Okay. Yes.
And,
yes.
and let me remind you, try to apply delta to a number and then you will see the problem. What is delta 2? And you will see the problem. Let's say x, I insist that x is an unknown and I know the value x is equal to 2, but you don't know the value x is equal to 2. For you it is an unknown, for me it is an unknown thing. Regardless of whether you know it or not, it is still a number, right? So delta of a number is nonsense. A number cannot change. And even if you want it to change, it will always be 0. So if you want to say that x is an unspecified number, then I'll say that delta x will always be 0 because it will always apply to a number and the number cannot change. You see the point? The only way to rescue yourself from this confusion is to remind yourself that x cannot be a number. It has to be a, say it, function. No matter how unusual you find it. And I know when you share this with your friends, they will be shocked, but I can't help it. I mean, this has to be, there's no other way.
Normally वही पढ़ाते हैं ना कि x जो है वो variable है और f of x
Huh? Yeah. So the thing which I learned from a French, he was actually living in the same apartment where I was preparing a presentation, and I went to him because he was a PhD student and I was master student. I asked him, okay, give me a tip. So he's told me, Mukhtar, you should know what you're doing. That's the only tip I want to give you. So you should know what you're writing. Yeah. When you write f of x, you should ask yourself, why we keep writing that thing? Because we never ask. You ask. So you ask and you will see the problem. Yeah. And don't go for, how many times I have seen this, how many books have I seen. No, the number of books cannot determine whether something is right or wrong. Yeah. You have to convince yourself. And I have to thank Lean for that. Remember, don't tell me that I'm a super genius. No. Lean was forcing me to question my own understanding. So without Lean, I would never have come to this conclusion. Because Lean won't even allow you to write. The moment you write something nonsensical, it will stop compiling. The problem with these languages like Python, MATLAB, R, that they accept every nonsense because they were written by people who themselves don't know what they're doing. So they accept any nonsense. Lean doesn't do that. So Lean will force you to rectify your understanding before you can write even one line of code. That's why it is used for hardware verification as well, yeah? Software verification, algorithmic verification. If you want to guarantee that a particular algorithm is giving the functionality which you claim, no amount of test runs can guarantee that. But Lean can actually provide that. So this is I have to thank Lean for that. Don't think that it's not easy. But because I have made an effort, I believe that you can follow this. Yeah, you can now work on it. Okay. So we are now clear. So the question we need to get to delta x. So what is good about x here, which makes it possible to define delta for x as well? Because x is also a function. We have to thank that for it. So we just need a bit of twisting, right? So the only difference between this delta f and that delta x is that this delta f has to act on x. There you just have to remember that x has to act on some other abstract domain, but that shouldn't stop you from defining delta x. So now if I now ask you, how should I define delta x? And then we also need to define delta y. So now I'll write delta x there and delta y there. So how should be delta x? And before I write the right hand side, I need to write these things as well. So delta x alone cannot tell me whether that delta x is here or here or here. So actually, let's say I have my A there and my B there. So I have to do the same thing. Okay, once you are comfortable, you can stop writing this A every time. I told you, in language we make many mistakes. But as long as we remember that this is informal language, fine. You will never do that in a court, yeah? So that's what I'm requesting you. You can drop this A later on, but now you have to take this head on, right?
delta x will be b minus.
So even that is not acceptable, because even with writing A, it is still a function. So it has to act on a change. That's same h. You start at A, you bring a change of h, so A becomes A plus h. So what is it now? There is no function, so you want everything on the x-axis, right? So that whole computation will be on the
x.
So rather than writing f of A plus A, you will write A plus h directly, right? So
a plus h
minus Yeah, so it is h. Bingo. Delta x. So it's just the identity function. It doesn't change the input. As expected, it doesn't change the input. So now we have given a precise meaning to delta x. You choose h, the change, at a point A, and delta x will spit out. It will just accept that h from you at A. So think of it as a family of functions. For each A, you will have a new function. So you can think of it delta x1, delta x2, delta x3. You pick one of them because you pick A. Then you apply that to a change h, and delta x because it has no function. So it will. So think of it as a, if you want to think of it as a function, it's actually the identical function, y equals x. Y equals. So delta x simply gives you the same thing without changing anything. Now, what is delta y? Now, here, this is tricky now. First, let me try this and I'll tell you. What should I write here instead of A? Once we do that, you will be convinced that defining delta y is not very useful. So we should only stick with delta x and delta f. Because if we want to define delta y, what should I write here? No, that number, because we do not want to lose that meaning. This is a coordinate, the type. This is also a. So the meaning cannot change from x to y. There is nothing special about y or x. I want this meaning to be retained for delta x, delta y, delta z, and so on. So what will this be? This has to be the point where f is evaluated at A. So it will be f of A. It will be. I cannot choose this point arbitrarily. And even if you want, you can call it B. You can just call this B. So maybe I can just write, let's call this B. Although we are using B here as well. So let's call this another, let's call this C, for example. So then what do you expect here? What must go in the bracket? Yeah, the change has to be on the y-axis. Even if you write h here, this h will not be on the x-axis but on the, because you cannot change the meaning when you go from x to y. Why? Because delta has only one meaning, at x on a function, regardless of whether that is x or y or f. So we cannot allow x and y to change what we mean by delta. So this will be, tell me, this, instead of this a, you will have f of a, and this will be, yeah, f of a plus h. So f, essentially we got the same thing. So it's redundant basically. We only need to define delta x, because this delta f will give me exactly the same thing. So that delta y is actually delta f in disguise, right? There's nothing special about that. So if we are clear about this, then there is, moving to df is just a piece of cake now. But there is one thing which we need to keep in mind. Think about it. Think about this thing. Yeah? This change, sorry. If you think about this change, so this is your h or delta x, yeah? And this is the change. I'm now informally calling it delta x. Because when I call it delta x, I'm not allowed to do that. Delta x is not a number. Yeah. So let's call it h. Or I can say this is what you get when you apply delta x to h, right? And this will be, so you get this change in y because of the function. So remember, this line is a secant line. So that will be the difference between delta and d. Whenever you apply delta, it will follow exactly how you define your changes. Because you defined h, you defined delta x in your way, you chose the points. Wherever that point is, it will simply go from here, go to there, change here, change there. That is what you call by. So now you can easily say that, informally speaking, delta y, apart from the fact that it is a function, it actually represents the change in this function, the actual change, because you are following the secant line. So it means that if you ask yourself, what is the domain of delta x, delta f? What is the domain of delta f? Let's say you fix this, okay? When you fix this, that doesn't become your domain. So the set of all those numbers and this computation has to follow the secant line. Now, when you want to move from delta f to df, the formula will be exactly the same, but you have to stick to the tangent line. You will not be allowed to choose any change anywhere else. Here we can choose any change. I don't care. I just have to dictate a value of h, and I don't care where I end up. I don't care whether this is secant line or not. There I have to remember, because df will dictate me to remain always on a. So I'll only be able to fix the value of a. For the value of b, I will always remain on the tangent line, which means that I will leave the function. I cannot remain on the function. Here I remain on the function. Why? Because that's my requirement. So now let's remove this diagram, change this diagram, and let's see what do we get. I'm now changing this. So, right? And let's choose one point here. And let's draw a tangent here. Which also means that this requires you to have worked out your derivative otherwise by using Newton methods or Leibniz methods. Because this is not about computation, this is about the meaning. So let's say you have worked out derivatives, you have worked out, you know where to draw the tangent line, just like I showed you in GeoGebra, and now it's the time to give meaning to df. So what do you mean by df? Because every tangent will be to the curve at a point. You cannot speak about a tangent unless you have decided, because at every point you will have a different tangent, right? So let's say I fix this tangent. So this is A, and let's call this point P, point P. And similarly, this will be f of A, yeah, f of A. So now I'll use the same formula. So think about df as a modification of delta f. So now let's define df. F is a function, d is an operator, it will act on the function, it will give us a new function, but this process has to be done at a fixed point, because without that you will not be able to distinguish between this tangent and. So I'll just write in the subscript A. So I'm defining the differential of f at A. And it is still a function. Even at A, it's a function. So it will now ask you for the input. What is the input? I can again give that change h. There is nothing wrong with it. But, so let's say this is the point, right? A plus h. So now tell me, where should I stop? There, I was required to find the point on the curve, because my domain was the secant line. Now my domain is the tangent line. I do not care where the function is. I will only care about the tangent line. So I'll just find A plus h at the tangent line. So now can you recall the slope of this tangent line? Is the derivative. That's what we mean by derivative. So I assume that you have worked out the derivative. the derivative of f at a, what is the notation for that? F prime of a. F prime of a. The derivative of f at a. That is the slope. So a is my first point. H is the change. Where will be the second point? It will be determined not by f, but by f prime. Just like I showed you in GeoGebra. F of a plus m times x minus a. So this h is actually your x minus a. So this point will be, so if this is f of a, that point will be, now I'm labeling it here. No, f of a plus h, you are going back to the secant. F of a plus h will be the value of the function at a plus h. But then you will be leaving the tangent line. You're not supposed to do that. That will be delta f. We want df. So now tell me, what is this value? You have to multiply this change with the slope. And the slope is f prime of a. So f prime of a times h. Read it very carefully. F prime of a times h. Why? Because df, now this is part of the meaning. df is by definition a replacement of delta where you stick to the tangent line. If you don't stick to the tangent line, then you are just using delta f. So the reason you are introducing a new concept is because you want to keep it on tangent line. So now what will be, now we have a definition, tell me. That is still wrong. What I wrote there is still wrong. Because that is the change. H is the change. Multiply the change by the slope is the change. The change has to be added to f of a. So that thing will be,
a plus f.
just because I'm writing something doesn't mean it will be correct, right? So you have to use your head as well. So f of a plus h, the change is h, this changes slope times h. So f prime of a times h is only the change. That change has to be added to f of a to give you f of a plus. So you can think, if you call this b, that is actually, can you call it f of b? No. You can't call it f of b. Because f of b will be the point on the graph, and that will be on the secant line. Remember, I told you in GeoGebra that you call it tangent when these 2 points coincide. So that second point has to be at a. So you don't try to find that second point on the curve. So f of b is not our option. Yeah, we have to remain on this line. So now tell me, what will this be? This will simply be this value minus this value, because you are sticking to the tangent line. So what is the change between these two? F of a cancels out, and you are only left with we have given a final precise definition to df. Differential of a function at a will take as the input any change you like. And remember, we are not requiring h to be small. We only require to remain on the tangent line. We don't care whether h is 1 or 100 or 1 trillion or 1 million. I'll get to the requirement of why do we want it to be small. There is another reason for that. Yeah, we don't care, tangent line. Now I'm here, I'm stressing on the definition. The definition does not require h to be small. The definition only requires you to be staying on the tangent line. So now you must be asking, why do we always talk about keeping h small? Because we want something else. And that something else has nothing to do with what we mean by df. We want df to be an approximation of delta f. That is now the application. Never confuse application with definition. We use calculus because we want to estimate certain changes. And in most cases, we don't have the full function available to us. If the function is available to me, I don't need calculus. I'll just say f of b minus f of a. So why I need calculus? Because most of the time, I only have information about the derivative. You know why? That's why you see differential equations everywhere. All the models you see in physics and chemistry and engineering, they're all the time differential equations, which mean that you will have information just like you are in the car, you're running, you're driving. What does the speedometer tell you? The speed, that's a derivative. The speedometer cannot tell you how far you have been driving. That is what you have to compute yourself. And if you want that to be done accurately, you would like this h to be so small that the calculation you get from df nearly matches the value you get from the actual function. So that is a requirement in the application. Do not mix that requirement with the. So what what Leibniz and his followers did, they mixed these two things basically. They made that requirement as part of the definition. That's why they were calling it infinitesimals. So the modern meaning of df, this meaning which I have given to you, is called the geometric interpretation of the differential. The problem here is that it is foolproof. There is no problem, but there is one problem. If you want to generalize this concept to more than one dimension, then there is a problem. Can you guess what the problem will be? So if you stick to single variable calculus, this is your friend. You have a precise definition of df. You know how to distinguish it from delta f, and you know that keeping it small is only a requirement. Let me just write this down. When you want df to be an approximation of, this is purely application driven, then you can say, you want to estimate errors, like how much error am I making in this computation? So that will require h to be small, but as far as the definition is concerned, all you require is to have the tangent line. So now the question is that if I want to export this knowledge to higher dimensions, then this is a problem. Why? Because in that case, both x and y will be independent variables, and your actual function will be on the z-axis. And in general, you can have n dimensions, x1, x2, x3. And then this limited concept cannot be generalized. So I'll just need to add that one last piece by redefining this, so that when you want to apply this to higher dimensions, you will have a more useful definition. So I'll now change this h. This a is still there. And I'm doing this only for df. I expect that you can do the same for delta f as well, because there is only, here you need to stick to the tangent line. There you can go on the secant line. So this does not need to be repeated. So because in multidimensional calculus, you will have to deal with vectors basically. So instead of defining it in terms of this, we have actually used a scalar h, because from here to here, if h is positive, this a plus h will be to the right? If h is negative, this a plus h will still be writing a plus h, remember? Because we allow h to be negative, so it will be a plus h. So, and h will be negative. But the problem is that this is the only thing you can do. So a scalar cannot allow you to come outside of this. So then you have to replace this with vectors. So let's say instead of this, I do something. I use a point P, and I say, okay, let's choose a point Q there. On the graph, this will be a change representing, a vector representing some change along the secant. And let's say if I want to stick to the tangent line, so let's call that, I'll just keep it there. I'll just call that, for example, q prime. So this will be a vector along the tangent. Now I have two vectors. I can have vectors along the secants, and I can have vector along the. So I'll now define this df for the tangent, and that the other thing you can do yourself. So this will be a function of any vector along the tangent. But that vector must have its tail. This is very important. Because when you specify a vector in school, you must have typically heard that you only need two things. The magnitude, that is incomplete. Because that misses the point of where you start. How can I distinguish between this vector and this vector? They have the same magnitude and the same direction, but they are different vectors for two reasons. They have different lines of action. You know why? When can you rotate something? I have this force upward, this force downward. So the vector sum of those two forces must be 0. So this thing should not rotate. There are two vectors on different lines. So to specify a vector completely, you need magnitude, you need direction, you need the line of action. And even that is not enough. You need the point of where you start. Even if I stick to the same line of action, these two are different vectors because they have different positions of the tail. So do you now realize why I gave importance to P? This P will determine where you start. The tangent line will dictate where to stay, line of action. You cannot have this vector elsewhere. And then, so this second point, q prime. So if this vector v, if you promise that this vector v will represent the change from that point P which I decided, I have freedom to choose that P anywhere on the curve. But once I do that, then the tangent line will dictate all the remaining points. So all the vectors v, so this vector can be small, this vector can be large, but I have to remain on the tangent line. Once I do that, and remember, I have to write here P, because I want this definition to be general. I don't want to write A. So P will be a point in multidimensional space. V will be a vector, maybe with n components. So now tell me, what should I do here? Yes? Line of action is the only reason why you can rotate things with two opposite forces. You cannot have equilibrium if you have two forces of, you remember Newton's third law says that for every action there is a, but that reaction must be in the same line of action, otherwise it's not a reaction. So two forces forming a couple and rotating the thing is not an action-reaction pair, right? It has to be on the same line. The problem is that in many school textbooks, they miss these important points, and then you carry that baggage throughout your life. So, okay. So once I do that, so what will I do here? I'll just here, because now I know the meaning of dx, dy. So let's say this is, just for your understanding, let's say this is a two-dimensional problem. So x and y are now independent variables, and the function is actually a surface. So let's say this is x, this is y, and this is z, and the function is actually a surface. So this right side will be constructed so that I gather those two things. Because now I will not have a tangent line, I will have a tangent plane. And you can only specify vectors in a plane if they have two components. Maybe a component along the x-axis, a component along the y-axis. So then I will have one, so with this line, you only needed one slope. Here you will need two slopes. One slope along the x-axis. So partial derivatives. So that slope, f prime of a, will be replaced with partial derivative along the x-axis. This will be the slope along the x-axis. That will multiply the change along the x-axis. No, x-axis, because this is the slope along the x-axis. So that change has to be derived from v. So it will be the x component of v. There you had h, because there was only one line and one change. Now you have one change along the x-axis, one along the y-axis, and v is the change vector, the change. So the x component of this v will be what you had h before. So that's why I'm not writing h, I'm writing v x plus. Just like when you are, let's say you are climbing. Huh? So when you are climbing, so let's say you don't want to go straight. So you say, okay, in order to go from this point to that point, first I go along the x-axis, then along the y-axis. So I'm now constructing that change. Now I need the slope along the y-axis. That same vector is now, no, vy. Vy means the y component of. Now I have a definition for the. So this is the final definition, because this is now applicable even to single variable. How? You just remove this part. Because if we now use the same definition to our previous problem, which was a single variable calculus, this will disappear because it's only one derivative. So this will be your f prime of a. But remember, where is that p coming from? So one thing is missing here. This derivative has to be computed at p. You cannot have just any partial derivative. It has to be at point p. And that also has to be, because remember, the point is important. Why? Because this slope has to be determined from a tangent plane. And every point will have a separate tangent plane. Right? Why? Why am I saying that? Because the vector v is only the change. The vector v cannot tell you which point of the curve you had a tangent at. V starts after that. Yeah? So now we have a complete definition. One thing which you must remember, this is strictly speaking not a definition. This is actually a definition that only works in Cartesian coordinates. So if you understand this, I'll now invite you to go home. You must be able to express this in polar coordinates as well. Similarly, you will have a derivative along the radial line and a derivative along the theta spherical coordinates. You can have any. So strictly speaking, you know the main concept. Yeah? So you can think of it as the, for those of who are comfortable with the language of multivariable calculus, the way we have defined the DF already has a name in multivariable calculus. But they somehow, only the computation matches. The concept, they have a different way of looking at it. Have you heard directional derivative? So you start with a scalar function and you differentiate it along a particular vector. This v is that vector. So if you have done any multivariable calculus, try to work that out, and these two will be numerically equal, but we are calling it the differential. They don't call it differential, they call it the directional derivative. Why it matters? The directional derivative in calculus is defined just as a single number, because they choose the point and they just find a single. Here we want to define this as a function. So this is the reason why I'll say that the similarity with directional derivative is only computational. Conceptually, it's a different thing. I think that was enough for today.
अच्छा आपने एक्सप्लेन किया। देखें जो प्रॉब्लम्स है ना वो समटाइम्स इंट्यूशन से आते हैं, और ये जो हम बनाते हैं ना फिज़िक्स की इंट्यूशन, ये इस वजह से ये प्रॉब्लम बनता है। ये बीच में जब आप स्केलर्स की बात कर रहे थे, स्केलर्स ही वेक्टर्स ही होते हैं। मैंने एब्स्ट्रैक्ट अलजेब्रा पीएचडी करी। आप स्टार्ट ही डिफाइन करते हैं वेक्टर्स, वेक्टर स्पेस की जो डेफिनेशन होती है ना, उसमें ये नहीं आप डिफाइन करते कि जी वेक्टर एक ऐसी चीज़ होती है जिसकी एक दुम भी होती है और एक सर भी होता है, ठीक है।
एब्स्ट्रैक्ट
आप एब्स्ट्रैक्ट वे में
अलजेब्रा
डिफाइन करते हैं।
एक्सटीरियर
उसमें आप एक सेट से ही शुरू करते हैं, सेट थ्योरेटिक डेफिनेशन ही होती है, और वहाँ सेट से फिर आप बाइनरी ऑपरेशन डिफाइन करते हैं जो बेसिकली एक फंक्शन होता है,
बिल्कुल बिल्कुल
ठीक है।
बिल्कुल
और फिर उनको आप एडिशन कर सकते हैं। हर सो कॉल्ड वेक्टर का इनवर्स भी होता है।
polynomial is also
हाँ जी,
vector
वो हाँ, वो पोलिनोमियल भी
yeah,
वेक्टर
my
होता है।
problem is that
ठीक।
when I was dealing with students I
जी।
couldn't expose them to that
तो ये एक्सपोज, इससे बचने का यही तरीका है कि उनको, जो कि हम एफएससी से शुरू कर देते हैं, ग्रुप थ्योरी के कॉन्सेप्ट समझाना, ठीक है। जब उनको वो कॉन्सेप्ट सही नहीं क्लियर होते ना,
तो फिर
तो
ये
वो
baggage
समझते हैं कि वेक्टर वही है जो फिजिक्स में है वेक्टर,
जो
ठीक है।
एरो है
हाँ जी, बस जिसका एरो होता है, ठीक है। पोलिनोमियल्स भी वेक्टर्स होती है, मैट्रिक्स भी वेक्टर होता है।
बिल्कुल।
इवन ये जो आप कह रहे थे स्केलर वेक्टर, ये स्केलर भी वेक्टर ही होता है। एक्स एक्सिस के ऊपर जितने पॉइंट्स होते हैं,
मैट्रिक्स इज अ वेक्टर,
मैट्रिक्स एक वेक्टर होता है, ठीक है।
बिल्कुल
तो ये प्रॉब्लम इस वजह से आते हैं क्योंकि लोग फिर कॉन्सेप्ट एब्स्ट्रैक्ट अलजेब्रा,
that is a root that is
हाँ,
one root of
वो एक रूट है। और जो डेफिनेशन हम करते हैं ना, उसी एब्स्ट्रैक्ट अलजेब्रा से ही शुरू कर देते हैं कि फंक्शन की डेफिनेशन आपने डिफाइन करनी है कि फंक्शन क्या होता है। पहले आप सेट से शुरू करते हैं, सेट से कार्टेशियन प्रोडक्ट डिफाइन करते हैं, ठीक है। फिर उसके ऊपर आप फंक्शन डिफाइन करते हैं, और वो उससे भी पहले थोड़ा आप पहले जाते हैं, आप रिलेशन डिफाइन करते हैं, ठीक है।
So maybe we can try
हाँ,
that,
अगर हम
that
उस
avenue, yeah.
हाँ उस
I wanted
डायरेक्शन
to
से
keep it I want to
जी।
keep it humble
हाँ, तो ये कैलकुलस का फिर ज़्यादा अप्रोच चूँकि ये इस तरफ जाती है। एक चीज़ आपने शायद मेरे ख्याल में ऐड की जा सकती है इसमें। मैथमेटिशियन इसमें आगे चल के जो डेफिनेशन करते हैं ना डेरिवेटिव की, वो भी विदाउट लिमिट एप्सिलॉन डेल्टा की डेफिनेशन से ही करते हैं, ठीक है।
वो तो मैंने assume किया था ना, जब मैंने ये कहा था कि आपको f prime of a पता है
जी।
so I had that process in mind।
और फॉर एग्जांपल मेरे पास अभी ये बुक है टोपोलॉजी की भी, तो टोपोलॉजी की सेंस में भी आप इन चीज़ों को,
if you can show it to the audience
देखें। एक तो सिंपल डेफिनेशन होती है ना, एक एप्सिलॉन डेल्टा डेफिनेशन होती है, क्योंकि ये प्रॉब्लम, ये जो इंट्यूशन के प्रॉब्लम थे ना, शुरू में कैलकुलस में डेरिवेटिव की डेफिनेशन नहीं बनी, बहुत अरसे बाद मैथमेटिशियन ने डेफिनेशन बनाई है। मतलब कॉन्सेप्ट जो न्यूटन और लाइबनिज वालों ने दिया है,
बिल्कुल
डेफिनेशन जो फॉर्मल डेफिनेशन है ना डेरिवेटिव की, और इवन
बिल्कुल प्रिसाइज वही है,
वो वही है जिसे हम
Precise वही है,
एप्सिलॉन डेल्टा डेफिनेशन
इसीलिए
कहते हैं।
मैंने उसको रिक्वायर किया कि I assume you have worked that out।
यस,
that
तो
was
अगर
important, yeah।
मैथमेटिक्स को इसलिए कहते हैं ना, थोड़ा फिजिक्स से थोड़ा सा हटके सेपरेट सब्जेक्ट के तौर पे पढ़ेंगे तो फिर ये कंफ्यूजन नहीं
क्योंकि
होगी।
मेन इशू ये आता है ना, क्योंकि आपकी वो पहली वाली बात से मैं 100% एग्री करता हूँ, ग्रुप थ्योरी, टोपोलॉजी और वो जो है ना
एनालिसिस, हाँ,
एब्स्ट्रैक्ट एनालिसिस। लेकिन ये दूसरे पॉइंट आपने बताया है ना कि लेट्स से एप्सिलॉन डेल्टा से हम डेरिवेटिव कंप्यूट करें, तो वो कंप्यूटेशन हो गई। ये dx
नहीं,
का
उसकी
मतलब
पूरी
हल फिर भी नहीं होगा।
नहीं, उसकी भी पूरी फॉर्मल
तो
डेफिनेशन
डिफरेंशियल
है।
फॉर्म्स,
हाँ,
तो ये जो मसला है ये बेसिकली डिफरेंशियल फॉर्म्स ने हल किया, जो डिफरेंशियल कैलकुलस है ना, जो डिफरेंशियल फॉर्म्स फिर से आए, और वो भी कहते हैं कि आपने एप्सिलॉन डेल्टा से अपनी डेरिवेटिव्स कंप्यूट की है। पार्शियल, देखो ना, मैंने पार्शियल डेरिवेटिव यूज किया, मैंने आई डिडंट से अ वर्ड अबाउट दिस, सो आई assume that same epsilon delta process of arriving at the partial derivatives, here the purpose was only to give meaning to dx and dy and df। तो ये थोड़ा सा
अगर मैथमेटिकल पर्सपेक्टिव से एज ए स्टूडेंट ऑफ मैथमेटिक्स, अब अगर आप स्टडी करेंगे ना जैसे मैथमेटिशियन करते हैं, फिर कोई कन्फ्यूजन नहीं है। ये आगे इंटरप्रिटेशंस की कन्फ्यूजन है, और इसका हल यही होता है कि जब आप किताब लिखते हैं तो आप शुरू में ही पहले अपनी नोटेशन फिक्स कर देते हैं कि भाई इसका मतलब ये है, इसका मतलब ये है, ताकि बाद में ये कन्फ्यूजन जो है
मुझे सारा मसला पता है किस चीज़ का हुआ था, जब आपको ये कहते हैं कि dy dx जब आप डिवाइड करते हैं, so it is not a ratio। So
I mean, this is
here we can show that it is a ratio of two functions।
देखें
You
यहाँ
can divide one function by another function।
जी, मैं इसको ऐसे देखता हूँ, ये रिप्रेजेंटेशंस हैं और फिर ये इंटरप्रिटेशंस के प्रॉब्लम है। ये फिलॉसफी के अंदर फिर हम चले जाएंगे, इंटरप्रिटेशंस हैं सारी की सारी, ठीक है, और रिप्रेजेंटेशंस हैं। अब जब हम एग्री कर जाते हैं किसी एक पर्सपेक्टिव के ऊपर कि ये हमारी नोटेशन होगी और ये उसकी रिप्रेजेंटेशन होगी और इसका मीनिंग ये होगा।
Meaning ये होगा,
जब हम
बिल्कुल।
उसको फिक्स कर देंगे तो फिर उसी हिसाब से चलेंगे और उसी लैंग्वेज गेम के अंदर मतलब वही सारी फिर हमारी लैंग्वेज होंगी और वो आसानी के लिए, क्योंकि अदरवाइज अगर आप इस तरीके से चलेंगे ना जैसे आपने किया, क्लैरिटी के लिए ठीक है, इट्स गुड टू नो कि आप जो कर रहे हैं, जो लिख रहे हैं
I
वो,
would
लेकिन
call
ये
it
है
a
कि
first
हम
exposure,
हाँ
first
यस
exposure है।
अगर लेकिन अगर आप इसको एज ए टेक्स्ट फॉर्म में लिखना शुरू कर देंगे इट विल बी कम्प्लीटली अगेन मोर, क्योंकि आपने थ्रू लैंग्वेज थ्रू अपनी नोटेशन किसी को अपनी बात पहुंचानी है कि भाई दिस इज माय आइडिया।
ठीक है, सही
अब अगर आप इसको बहुत ज़्यादा कॉम्प्लिकेटेड कर देंगे लैंग्वेज के उसमें ही तो
ठीक
वो
है।
फिर और प्रॉब्लम हो जाएंगे। उससे ही बचने के लिए आप फिर स्मॉल नोटेशंस मिनिमम नोटेशंस की तरफ आएंगे। उसका हल यही है कि पहले बच्चों को या पहले जो स्टूडेंट्स जो भी है वो पहले अपने बेसिक कॉन्सेप्ट्स क्लियर करें कि सेट क्या होता है, फंक्शन क्या होता है, ताकि उसको पता चलता जाए कि किस जगह पे किसका क्या मतलब है। तो वो चूंकि क्लियर नहीं होता ना, फंक्शन की डेफिनेशन ही क्लियर नहीं होती। और मैं आपको बताऊं, मैंने एमफिल लेवल पे स्टूडेंट्स को इवन इंटरव्यू करते हुए पूछा कि फंक्शन क्या होता है, उनको
तो
पता नहीं
आपको
होता।
लगता है कि जो मैंने स्टार्ट में बहुत ब्रीफ एक्सपेक्ट किया कि आप तीन चीजें हैं, नंबर है, सेट है और फंक्शन है।
जी बिल्कुल, आपने सही किया।
नहीं, वाज दैट टू मच टू आस्क फ्रॉम द
नहीं,
ऑडियंस?
वो बिल्कुल सही है।
अच्छा।
वो ही होना चाहिए
अच्छा,
कि
अच्छा,
अर्ली
अच्छा।
स्टेजेस पे, और ये चीज़ हम मैट्रिक से शुरू कर देते हैं। ठीक है, आपको मैट्रिक में और वो डेफिनेशन पहले चैप्टर छोड़ देते हैं बच्चे। ठीक है ना, टीचर छोड़ देते हैं, वो कहते हैं जाओ चलो डायरेक्ट सॉल्व करें। फिर एफएससी में आते हैं तो वो कहते हैं जी ये फंक्शन है, साइन एक्स है तो इसका डेरिवेटिव, अरे कॉज एक्स है जी, टेंजेंट एक्स का डेरिवेटिव है, ये निकाल लें, इंटीग्रेशन। तो कॉन्सेप्ट्स पहले ही डेवलप हो रहे होते हैं। तो फंक्शन का ही कॉन्सेप्ट नहीं है, सेट का ही कॉन्सेप्ट क्लियर नहीं है, तो फिर आप आगे उनको कैलकुलेशंस पे लगा देंगे तो फिर
हाँ, वो
मिस्टेक्स हो
था
जाएंगी।
क्योंकि
तो
फंक्शन
बाकी इसमें ये जो एनालिसिस की बातें हैं ना, ये
एप्सिलॉन डेल्टा वाली चीज तो
उसमें
है।
फिर एक और
मैं
चीज
उस तरफ
आती है।
जाना नहीं
हाँ, ये
चाहता
जो
था ना।
डिफरेंस आप कह रहे हैं ना, इस डिफरेंस को भी इन टर्म्स ऑफ फंक्शन आप डिफाइन कर सकते हैं। उसे हम कहते हैं मीट्रिक। वो मीट्रिक स्पेसेस में आप चले जाते हैं।
बिल्कुल,
ठीक है, वो
बिल्कुल।
एनालिसिस
टोपोलॉजिकल
और
इसमें
हाँ,
आता है,
और मीट्रिक से आगे फिर वो टोपोलॉजिकल स्पेसेस में आप चले
टोपोलॉजिकल
जाते
स्पेसेस है,
हैं।
बिल्कुल।
तो ये पूरे एक वेल डिफाइंड कोर्सेज हैं
असल
जिससे जिन स्टेप
मेरी
से आप इन चीज़ों
मेरी
को।
बाइस शायद उसकी एक वजह ये भी है ना कि आई एम डीलिंग प्राइमरीली विद इंजीनियरिंग स्टूडेंट्स।
जी जी, थैंक यू।
So I was addressing most of their confusions. So I don't think I will be able to bring them to topology or group theory. I mean, I will start thinking along those lines as well. Maybe we can have a session on that as well. But yeah, so far I have this differential forms. फिलहाल ये जो है ना doable था मेरे लिए।
अच्छा, मैं लैंग्वेज के हवाले से यही तकरीबन बात करना चाह रहा था जो नकीब साहब ने की,
जी जी।
कि ये आपने लिखा कि व्हाट डी एक्स एंड डी वाई रियली आर। तो लैंग्वेज में तो रियली तो कुछ भी नहीं होता, ये सब आर्बिट्ररी होता है और मीनिंग वही होता है जिस पे सब ने एग्री किया
एग्री
होता है।
करना होता है, बिल्कुल।
तो अगर एक मेजॉरिटी ने किसी चीज़ पर एग्री किया हुआ है तो आप नए सिरे से यू कांट हैव योर पर्सनल मीनिंग्स। आपको
Yeah, but this has been agreed. जो मैंने पैराग्राफ शेयर किया था ना,
जी जी
वहाँ पे उसने नीचे लिखा था, maybe I can show that again. What I explained to you is actually there are two ways to solve this problem. One is this differential form concept, and there is another alternative to this. So the majority of mathematicians have settled on this f dx dy. There is another alternative which both of us actually missed, that is called the measure theoretic approach. So that is also an alternative, but I think that would have been too much for the audience. So ये agreement mathematicians की ही है, and they have actually settled into these two channels. This is one way of interpreting the differentials. So and there is even a third one, but that is actually something which is too complicated, and that is called the non-standard analysis. So they have their own interpretation of dx and dy. They think of them as hyper numbers. But to introduce the audience to something called the hyper number, so hyper number is not a number, it is a sequence. So how they get to zero? Remember, you are approaching zero, you are making it smaller and smaller, but you are not supposed to touch the zero. But you don't want to miss all this sequence. So they say that, okay, you start from any value less than 1, right? Because less than 1 can safely be called small. So less than 1 all the way, and make it smaller and smaller and smaller. So this whole sequence of numbers, they give one name to this. They call it the hyperreals. So hyperreal is a sequence of numbers. So the symbol, so what they stress is that the dx, the symbol dx, will not represent one number, but this whole sequence of numbers, which can go as closer to zero as possible. But the problem with non-standard analysis is that I have to learn it myself, and I haven't done so far, and I think it would have been too much for the audience. So there are mainly three, I would say, three schools of thoughts in modern mathematics. The infinitesimal interpretation, which was dictated by Leibniz and Newton and all that had been completely replaced with the 20th century mathematicians. That was the point.
नहीं, लेकिन मैं ये कह रहा था कि अगर एक तो उसकी एप्लीकेशन में कोई फ़र्क नहीं पड़ता, कैलकुलेशन में कोई फ़र्क नहीं
बिल्कुल
पड़ता।
बिल्कुल।
अब जैसे आप इमेजिनरी नंबर का जिक्र कर रहे थे, आप ठीक है इमेजिनरी गलत है, नहीं कहना चाहिए, लेकिन आप उसको लेटरल कह लें जैसे गाउस ने कहा था,
बिल्कुल बिल्कुल।
तो फ़र्क क्या पड़ता है? बात ये है कि अगर एक बानी पे आपने इत्तेफाक कर लिया है तो वो मीनिंगफुल है। उसके लिए जो अपेरेंट फॉर्म है वो आप इमेजिनरी रखते हैं उसके लिए या लेटरल कहते हैं। इन आइदर केस, इन आइदर केस लैंग्वेज के एतबार से उसमें कोई फर्क नहीं पड़ेगा।
In modern complex analysis, the mathematicians have agreed on the interpretation of I as a pair of numbers, 0, 1. So this is now agreed. What I was trying to convey that this 0, 1, as seeing the imaginary unit as a pair of numbers, is a very later development. The guy who introduced I, he was not aware of it. So it can happen. It can happen to me, it can happen to you as well.
नहीं, ये शायद ये कहना चाह रहे हैं कि जो इमेजिनरी नंबर्स होते हैं ना, वो भी जैसे रियल नंबर्स भी इमेजिनरी होते हैं बेसिकली।
बिल्कुल बिल्कुल, वो तो है, वो तो एब्स्ट्रैक्ट हो गया ना।
ये तो ये फिलॉसफी में फिर चले जाएंगे कि ये रियलिज्म और फिक्शनलिज्म है।
उसको फिर
ठीक है, रियल नंबर्स भी इमेजिनरी होते हैं।
उसको रियल को भी इमेजिनरी कहना चाहिए था ना। मतलब मसला ये था कि आप इसको रियल कह रहे हैं, इसको इमेजिनरी कह रहे हैं, तो दैट वाज अनफेयर। दैट वाज द पॉइंट।
कुछ इसको ऐसे भी रिकंसाइल करते हैं कि कॉम्प्लेक्स नंबर्स जैसे आप करने की कोशिश कर रहे हैं कि कॉम्प्लेक्स नंबर्स भी रियल ही होते हैं।
रियल ही होते हैं, बिल्कुल बिल्कुल। दे आर एज रियल। So the
as real as real are.
I is as real as 1.
ठीक है, बट फिलोसॉफिकली रियल जो नंबर्स हैं वो असल में इमेजिनरी हैं, क्योंकि हमने इन रियलिटी उनको देखा नहीं है। वो ये हमारी कंस्ट्रक्शन ही है। तो ये फिर वही फिलोसफी।
अलग टॉक मैंने ऑलरेडी दी थी साहब को, सेट थियोरेटिक कंस्ट्रक्शन नंबर्स की मेरी एक टॉक है यहाँ पे, जिसमें आप नंबर यू क्रिएट नंबर्स फ्रॉम नथिंग। मेरे ख्याल में आपसे पहली मुलाकात उसी में हुई थी ना, कि यू क्रिएट जीरो फ्रॉम द एम्प्टी सेट एंड देन यू, तो लेकिन वो तो है, वो तो अपनी जगह पे अपनी वो है, ठीक है। लेकिन मैं आई विल रिपीट अगेन दैट these three lines of thought to give meaning to differentials, I think this has been more or less agreed now.
There could be क्योंकि ये इंटरप्रिटेशंस होती हैं
और ये 1950 के बाद इसकी शुरू हुई है। 1950 के बाद जो बुक्स लिखी गई है ना, उन्होंने ये चीज़ चेंज करना शुरू कर दी। और ये how I got to know, don't expect me to read all those calculus textbooks. I got exposed to this only because of lean. Because when you write dx in lean, it will not even let you do that. So वहाँ पे वो आपसे पूछेगा कि टाइप क्या है। तो अगर आप dx, क्योंकि लीन में एक स्टाइल होता है ना, मैं यहाँ पे लिख देता हूँ, लीन में जब भी आप एक वेरिएबल लिखते हैं ना x, तो यू हैव टू डिक्लेयर द टाइप। सो लेट्स से अगर मैं कहता हूँ कि x लेट्स से इंटीजर है, सो आई हैव टू राइट दिस। जब तक मैं ये नहीं लिखूंगा, लीन को ये नहीं पता चलेगा कि ये रियल है या इंटीजर है या नेचुरल है या पॉजिटिव है। तो जब आप वहां पे dx लिखते हैं और अगर आपने वहां पे लिख दिया कि ये रियल नंबर है, so it won't even compile. So it will and lean is now widely used for theorem proving. तो उन्होंने बेसिकली यहाँ पे आपको फिर ये डिक्लेयर करना पड़ेगा कि इट्स ए कोऑर्डिनेट फंक्शन। तो वो मैं उससे मुझे थोड़ी सी इंस्पिरेशन मिली कि शायद इसको आजकल वैसे ही लोग AI टूल्स की तरफ जा रहे हैं। बिल्कुल
सर, शुक्रिया।
थैंक यू।
इसी डायरेक्शन में है मेरी सबमिशन कि मैं तो बुनियादी तौर पर फिजिसिस्ट हूँ।
जी जी।
मेरे लिए बहुत आसान है एक वेरिएबल को इक्वेशन लिखना,
ठीक है,
किसी फिजिकल फिनोमिनन से, और फिर उसमें जो चेंजेस आ रही हैं उन्हें एक्सप्रेस करना मैथमेटिकल टूल्स को यूज़ करते हुए।
ठीक हो गया।
ठीक है ना, मैं आसानी के साथ मौसम, प्रेडिक्शन, फोरकास्ट, अभी एआई में बड़ी आसानी के साथ मैं डिफरेंट वर्ड्स की पोजीशन अपने पूरे पुराने कंसेप्ट से कर सकता हूँ। मुझे कोई कोई प्रॉब्लम नहीं है उसमें।
ठीक है,
आपके जो इंतहाई मुश्किल तरीके से ये डेफिनेशन समझना है, मुझे
ठीक है।
किस तरह फायदा देगी ये?
Yeah, it's a very pertinent question. I would again refer to lean. So people are using lean for because now in this age of AI, many of the jobs which humans were actually doing, they are now disappearing because there are AI engines which can actually write code for you. So let's say you are a modern day developer and you write a program or you write a mathematical algorithm, right, to solve a problem. So people will ask you for guarantees of how of whether this algorithm or whether this program will give them the functionality which you claim. So the typical computer science or software engineering approach so far has been to have test runs. Yeah, you have many test runs. You imagine all the possible inputs which someone could give to that algorithm, and then they claim, okay, this is the I can now claim that this will give me the functionality. But now recently, especially the mission critical systems, they require proofs, mathematical proof that the claim that this algorithm will give me the functionality and this will not give me any surprises. For example, you can apply it to health and flight systems and so on and so forth. So that guarantee can only be given by software tools like Lean. And they are very particular about types. So whenever you want to take your mathematical formulas to Lean, they will actually then you will realize the issues. So there the meaning is very important because type is just a computer science name to meaning. Yeah, we say this is an integer, this is a real, this is complex. These are just types, and type is the meaning. So I think
सही
what you explained is only valid when humans were doing the coding things, and now the demand from humans is more intellectual than you are exposed to.
तो जो मैं अपने समझने के लिए दोबारा दरखास्त कर रहा हूँ कि योर ये जो जो कुछ भी वजाहत हुई है ये है कि हाउ वी इनपुट डेटा टू ए कंप्यूटर प्रोग्राम टू फॉर्मली वेरीफाई एन एल्गोरिदम और थ्योरम।
Yes.
ये जगह है जो फोकस कर रहे हैं आप?
नहीं, ये नहीं है. I'll give you a quote from Einstein, right? So he once said that you don't, if you can't explain it to a 6 years old, you don't understand it yourself. मसला ये है कि you can solve a problem and you still will not be knowing what it means because meaning is an entirely different thing. I told you already that there have been examples in mathematics where people were using things and they were not clear about the meaning. There is even a story about this guy from India, Ramanujan. No, sorry, this story is not about Ramanujan. This is about Bose. Bose, you know the Higgs boson. So that boson is from Bose, and Bose was an Indian mathematician. He wrote a letter to Einstein, and in that letter he actually proved something, and he was not convinced. He said that this should not work, and I don't know why I get the correct answer. So he sent that letter to Einstein. Einstein read that proof, and it took him 3 days to figure out. He actually made 2 mistakes. And those mistakes were in succession, they cancelled each other, and there was the correct answer. So you can make 2 mistakes, still get the correct answer. It means that you still don't know what you're doing. So I would highly actually request that modern day mathematicians, if they want to make a difference in the age of AI, they have to be exactly clear what they mean by what they write. If you're writing dx, and if you say this is a number, and then I ask you, okay, d2, what is d2? You will say 0. So you will get 0 every time. So that whole building of calculus crumbles down the moment you are confronted with software. That is all I'm requesting.
Another question. First of all, I'm really curious about this programming language. क्योंकि जब भी आप आते हैं सेशन
Lean, yeah. It's not a language, it's much more than that.
Okay, but I really want to know that क्योंकि if that thing is actually endorsing or forcing you to dive deeper into the mathematics,
Yes, of
that
course.
I really
yeah.
want to learn that thing. तो इसके बारे में थोड़ा सा गाइड कर दीजिएगा. सेकेंडली मेरा एक क्वेश्चन है, ये जो आपने ग्राफ बनाया था जिसके अंदर हम टेंजेंट लाइन को हम एफ प्राइम ए से डिनोट कर रहे हैं.
नहीं tangent line को f prime ऐसे नहीं करते.
Okay.
F prime of A is the slope of that tangent line.
Okay. So
That is not enough to specify the tangent line. Tangent line needs actually one point. You will have a tangent line at each point. So if I choose that point here, I will have a different tangent line.
yes.
So just knowing the slope will not be a complete characterization
क्या
of the
मैं
tangent
एक
line.
और वर्ड्स में या दूसरे वर्ड्स में ये कह सकता हूँ कि अगर मुझे टेंजेंट लाइन पर मूव करना है तो वो एफ प्राइम ए से हमें
F prime A can help us.
ठीक
Yeah,
है.
yeah. But we have to start with P.
यस.
Yeah.
तो मेरा क्वेश्चन ये है कि फिर आपने एफ प्राइम ए को जो डिफरेंस है एच से मल्टीप्लाई किया
Yes.
और फिर आपने उसको जो वाई एक्सिस है
Uh-huh.
उस पर एफ ए से ऐड करके शो कर दिया. तो क्वेश्चन ये है कि आपने एफ प्राइम ए को एच से मल्टीप्लाई क्यों किया?
अच्छा ठीक है. So that's exactly what we mean by slope. Yeah. So the meaning of slope is that along the line, take any 2 points. So the run and the rise. Yeah, rise is the change along the vertical axis. Run is the change along the horizontal axis. The ratio of these two is what we mean by slope. So in this case, we know the run, and we want to compute the rise. So slope times run will give us the rise,
ओके फाइन.
but only the rise. So that's why we have to add f of a to it.
ओके, अब आप थोड़ा सा लीन लैंग्वेज के बारे में बता दें.
Lean का ये है कि lean is a free tool. The good thing is that you don't need to pay for it, but you need to invest actually some intellectual effort. Online is also available. You can also install it in VS Code if you have heard VS Code, and maybe I can actually conduct a whole new seminar on that. I mean, so far I am not. I mean, I have not decided because lean के लिए, I mean, जब तक आप बहुत ज़्यादा curious नहीं है तो it will not be helpful to many. So it's a very serious thing. So if if I get to know that, I mean, a critical mass of the audience is interested in that, I can prepare. We will actually write some proofs in it, and we will actually solve things, and we can even do logic. So the logical propositions can also be verified in Lean. We can have one seminar on that.
और ये लैंग्वेज हम किस लिए ज़्यादातर यूज़ करते हैं? एप्लीकेशन इसकी क्या है?
It is used for verification, software verification. And software verification means proving that your software will work, not that hopefully it will work. Because what the current programmers are doing, they are only so they will fool the customer by numbers. I have tested 1 million different inputs. Yeah, even if you say 1 trillion raised to the power of 1 trillion raised to the power of 1 trillion, even that is not enough. Mathematically, you have to prove that it is the correct function, and it will not give you surprises. So lean is actually the reason mathematicians started using lean is that the traditional way of proving. I'll give you one example from Imam Ghazali, right? So you must have heard something about Imam Ghazali, that at that time he mastered all the body of knowledge relevant to Ilmul Kalam. Can you say that today? Can you expect a mathematician to master all the mathematics that has been done so far? It is literally impossible. So that is where lean comes into play. So what they do is that they have represented all the proofs done so far by mathematicians into modules. So you only need to read a paper and you say, okay, there this proof. You will actually call that proof as a package, and you can build on the work of other mathematicians without reading those proofs. So I mean, I would say it's a very practical tool. You can do math without getting through all that trouble. Yeah, but the thing is that it needs a change in perspective. If you want to do it in a traditional way, it will never work. So my main focus, I mean, this was only about dx and dy. So you should not think about dx and dy only. My request is that whatever you write in math, you must know what it means. Dx and dy are not special. Everything you write must have a meaning. So, and if you don't know the meaning, then you will face trouble using lean. That is the main argument, basically. Yeah. Yeah.
जिससे मैं ये पूछना चाह रहा था कि सर अगर हमारे पास एक स्टेटमेंट हो कि देयर इज एन एंटिटी ई, अगर स्टेटमेंट है कि हमारे पास एक एंटिटी ई है, तो आप कैसे इस बात को क्लैरिफाई करेंगे कि हाउ कैन वी एक्सप्रेस दिस एंटिटी इन टर्म्स ऑफ मैथमेटिक्स?
No, that you have to specify what that entity E is. So
General-
you have not. So you have not specified the type.
जनरल एंटिटी is
Yeah. So if I now get to this, if let's say you get to lean, right?
Yes.
So lean has a type hierarchy. So you build from, let's say, numbers and then reals, integers, reals, sets, functions, yeah, functions of functions, operators, matrices, all that. So when lean asks you for a type, he wants you to be clear. So if you say E is an entity, you actually want to tell lean that it can be of any type.
Yes.
So on its surface, there is nothing wrong with it, but I doubt if you can do anything useful with that E.
Right, sir. Thank
Because all the language of math is built on types. So for example, when I say A plus B, this A and B can either be numbers, because plus requires that. They can either be functions, they can either be matrices, but they cannot be two triangles. You cannot say a triangle plus a rectangle. That is a meaningless thing.
So it means that lean cannot handle
No,
general
no.
type of entities.
No, lean decided not to handle.
Yes.
Because lean knows that the developers of lean, they know that useful mathematics requires you to be specific about types. So if you say let E be a shape, for example, it can be any shape.
Yes.
But when you say a shape, you are ruling out E to be interpreted as a number, for example. Yeah.
Right. Thank you.
Yeah. Thank you.